Hey everyone, so now we are starting Merkle tree. Actually, while reading the theorem docs, I just got stuck into a topic that said that you must know Merkle tree before proceeding into this. So I'm continuing with Merkle. Just support me. Hooray! Merkle tree. What do you think is Merkle tree? You don't know? Let's read. Okay, a Merkle tree is a hash-based data structure that is a generalization of the hash list. It is a tree structure in which each leaf node is a hash of a block of data. It is a tree structure in which each leaf node is a hash of block of data and each non-leaf node is a hash of its children. अरे भाई समझ गया. There are many blocks. Suppose there are 8 blocks. What we are doing? We are just pairing them. We are just assigning leaves to it. We are just hashing them, storing the data into leaf nodes. What we are then doing? We are just making a tree structure formatter uh, and hashing these two hashes into the upper parent node, and this way we will get 8 nodes, then 4 2 1. Okay, fine, got it. बहुत easy है Merkle tree. Merkle tree are used in distribution system for efficient data verification. They're efficient because they use hashes instead of full files. Merkle tree are used in distributed systems for efficient data verification. They are used for data verification. Like if you'll tamper with any one of these block files, then the Merkle tree hash will be totally different. So you can't tamper with the data. That's a thing that for which Merkle tree are used is used. Hashes are a way of encoding files that are much smaller than the actual file itself. They are efficient because they use a hash instead of full files. ठीक है, hash is a way of encoding files that are much smaller than the actual file itself. Currently, their main uses are in peer-to-peer networks such as Tor, Bitcoin, and Git. अरे, Git also uses Merkle. Whoa. Peer-to-peer network. Tor. Tor browser. Have you used? I have not. Would you? Merkle tree are typically implemented as binary trees. Binary trees. What are binary trees? These are the trees where a node have at max two child nodes. Merkle tree typically implemented as binary trees, as shown in the following image. However, Merkle tree can be created as an n-ary tree with n children per node. Okay, n-ary tree can also be formed, but generally we form an binary tree. Means each node have two children. Fine. Data blocks, fine. Got it. Actually, you can see this image in order to relate if it's visible. Yeah. In this image, we see an input of data broken up into blocks labeled L1, though L4. Each of these blocks and hashed using some hash function. Then each pair of the nodes are recursively hashed until we reach the root node, which is the hash of all nodes below it. Each pair of each of these blocks are hashed using some hash function. Using some hash function, we are hashing all the data in this node, and what we're doing after it, then each pair of nodes are recursively hashed until we reach the root node, which is the hash of all nodes below it. The hashes are then recursively hashed on pairs such that we'll ultimately reach to a single root hash. Oh, okay. The root hash that we were reading earlier in the block section. I think it got clicked in my mind. Then each pair of nodes are recursively hashed until we reach the root node, which is a hash of all nodes below it. इससे क्या हुआ that validation checking कि if you tamper any data inside the block, then the root hash will change, and ultimately it will be shown that the data has been tampered. Benefits and protocol. In various distributed and peer-to-peer system, data verification is very important. This is because the same data exists in multiple locations. In various distributed and peer-to-peer system, data verification is very important. This is because the same data exists in multiple locations. So, if a piece of data is changed in one location, it's important that the data is changed everywhere. Data verification is used to make sure that data is same everywhere. Acha. So, if a piece of data is changed in one location, it's important that its data is changed. Oh, isn't it something different? In various distributed and peer-to-peer system, data verification is very important. This is because the same data exists in multiple locations. Yeah, however, it is time consuming and computationally expensive to check the entirety of each file whenever a system wants to verify data. So this is why Merkle trees are used. However, it is time consuming and computationally expensive to check the entirety of each file whenever a system wants to verify data. So this is why Merkle trees are used. Basically, we want to limit the amount of data being sent over a network like the internet as much as possible. So instead of sending an entire file of the network, we just send a hash of the file to see if it matches. The protocol goes like this: computer sends a hash of the file to computer B. Computer B rechecks the hash against the root of the Merkle tree. If there is no difference, we are done. Otherwise, go to step 4. If there is a difference in a single hash, computer will request the roots of the two subtrees of that hash. Bhai Saab, I got the point. I got it. I got it. If there's a difference in a single hash, computer V will request the roots of the two subtrees of the hash. Computer creates the necessary hashes and send them back to computer. We repeat step 4 and 5 until you found the data blocks that inconsistent. It's possible to find more than one data blocks that is wrong because there might be more than one errors in the data. हाँ ठीक है. मतलब ultimately the thing is, why are we creating Merkle trees? Why are we creating Merkle roots, Merkle hashes? So that in order to verify the data that computer A also have, that computer B also have, but we don't want to send the entire data from computer A to computer B so that the computer B will be able to verify that. What we are doing is we are creating a Merkle root of the data and we are sending only the root to this node, and if it find it equal to the root hash of the Merkle tree of its own data, then yeah, they are both equal, exactly the same. Otherwise, if not, it will computer B will ask computer A that hey root, just send me the hashes of two children of that root node, and ultimately it will find in this way that which part of the data is corrupt or that is different from that present in computer A. So sorry. Note that each time a hash is found to match, we need n more comparison at the next level. Each time a hash is found to match, we need more comparison at the next level where branching. The algorithm is predicated on the assumption that network takes longer than local I/O to perform hashes. This is especially true because computer can run in parallel calculating multiple hashes at once. Predicated on the assumption that network input output takes longer than local I/O to perform hashes. Because the computer are only sending hashes over the network, not the entire file, the process can go very quickly. Plus, if an inconsistent piece of data is found, it's much easier to insert a small chunk of fixed data than to completely rewrite the entire file to fix the issue. The reason that Merkle trees are useful in distributed system is that it is inefficient to check the entirety of file to check for issue. The reason that Merkle trees are useful in peer-to-peer system is that they help you verify information even if some of it come from an untrusted source, which is a concern in peer-to-peer system. Hmm. The way that Merkle tree can be helpful in a peer-to-peer system has to do with trust. Before you download a file from peer-to-peer source like Tor, the root hash is obtained from a trusted source. After that, you can obtain lower nodes of the Merkle tree from untrusted peer. All of these nodes exist in the same tree-like structure described above, and they all are partial representation of the same data. The nodes from untrusted source are checked against the truthed hash. If they match the truth hash, meaning they fit into the Merkle tree, they are accepted and the process continues. If they are not good, if they are no good, if they are no good, they are discarded and searched for again from a different source. Use case. As stated above, Merkle tree are especially useful in distributed peer-to-peer system. Where is this Merkle tree being used the most? These are mostly used in distributed systems and peer-to-peer systems where the data where the same data should exist in multiple places. Concept of Merkle tree is useful when we want to check that the same piece of data is present at different locations by just not sending the entire file and just sending a hash. These systems use Merkle tree or variants from Merkle tree in their implementation. Git, the popular version control system mainly used by programmers. All the saved files are saved on every user's computer at all times. All the saved files are saved on every user's computer at all times. So it's very important to check that these changes are consistent across everyone's computer. Bitcoin is a popular online anonymous currency. All transaction bitcoins are stored in blocks on what is called the blockchain. All transactions in Bitcoin are stored in blocks and what is called blockchain. The blockchain exists on every Bitcoin user's computer. Leaves of a Merkle tree used in Bitcoins are typically hashes of single blocks. Every time someone wants to alter the blockchain, for example by adding transactions, this change needs to be reflected everywhere. Hmm. Merkle tree ईवीएम भी यूज कर रहा है मतलब Merkle tree can be used to check for inconsistencies in more than just files and basic data structures like the blockchain. Means Merkle tree can also be used for complex data structures like blockchain. Apache, Cassandra, and other NoSQL systems use Merkle trees to detect inconsistency between replicas of the entire database. Cassandra. Uh, I have read about Apache Cassandra. Like it's also a distributed service provided by Apache and other NoSQL system like Mongo and all that systems. We use Merkle tree to detect inconsistency between replica of entire database. Imagine a website that people use all over the world. That website probably need database and servers all over the world so that load times are good. If one of those databases get altered, then every single other database needs to be altered in the same way. Hashes can be made of chunks of the database and Merkle tree can detect inconsistencies. Imagine a website that people use all over the world. That website probably need database and server all over the world so that load times are good. That is probably need database server all over the world so that the load times are good. If one of the database gets altered, then every single other database needs to be altered in the same way. बात तो है. Hashes can be made of chunks of the database and Merkle tree can detect inconsistency. Now, this is the day when I totally understand what Merkle tree do and why is it used. I hope that you also understand the same complexity. Merkle tree have very little overhead when compared to its hash list. Binary Merkle tree, like the one pictured above, operates similar to binary search tree in that their depth is bounded by their branching factor. Second, included below is the worst case analysis for Merkle tree with a branching factor of k. Amortized, however, very important aspect of Merkle tree and their biggest use case is the synchronization of data. In the typical case, the synchronization will be a log 2 of n, log 2n, log to the base 2 and log n to the base 2 operation because it is based on traversal and search. However, there is a worst case situation where there are no nodes in common. In this scenario, synchronization is akin to making a complete copy of the file, which will be a big of an operation. Ha, fine. So this completes our Merkle discussion. I hope you must also understand it that what exactly Merkle tree are. Now let's again jump to our Ethereum doc section. Fine, bye.